December 1942. Richmond, California. The night air trembled with the sound of hammers, welders, and rolling cranes. Beneath the floodlights, sparks fell like orange rain across rows of unfinished Liberty ships, hulking silhouettes of steel stretching toward the bay. It was near midnight, but no one was resting. Men in helmets and women in overalls worked shoulder to shoulder, arcs of molten light flashing across their faces. A whistle blew, a foreman shouted for clearance, and one more whole section slid smoothly into alignment, fitted not by hundreds of rivets, but by an unbroken weld that glowed like liquid silver. In that moment, the old world of shipbuilding vanished. What had once taken half a year could now be done in days. No blueprints changed, no engines redesigned, only a method, a daring shortcut conceived by a civilian with no naval rank. The ocean would soon fill with his work, and the war would turn on the speed of his sparks. The WWII early 1941. The world's oceans had become graveyards of steel. German U-boats prowled the Atlantic with ruthless precision, sinking merchant convoys faster than they could be replaced. Britain, isolated and desperate, relied entirely on the sea, and every torpedoed freighter meant one more line of supply severed, one more ship that would take months to rebuild. America had not yet entered the war, but it could already see the arithmetic of disaster forming offshore. If the Allies were to survive, they needed a fleet that could multiply faster than the U-boats could destroy it. The solution came from the United States Maritime Commission, a program of standardized cargo ships, designed to be cheap, functional, and, above all, fast to build. They would be called Liberty ships, a name simple enough to fit the purpose. The first design, the EC2 C1, was neither elegant nor glamorous. It was squat, box-shaped, and slow, but it could carry 10,000 tons of cargo across the Atlantic. The idea was clear: quantity over beauty. In war, speed of production would be the new measure of power. Yet speed was the very thing shipbuilding had never known. Before the war, constructing a cargo vessel was a craftsman's ritual, months of riveting, fitting, testing, and re-riveting. Each steel plate was drilled, aligned, and hammered by hand, with tens of thousands of rivets sealing every joint. The process was reliable but agonizingly slow. Even the most efficient yards took over 200 days to launch a single ship. At that rate, the math was unforgiving. For every Liberty ship completed, the Atlantic claimed 3. In Washington, officials scrambled for answers. They needed more than shipyards. They needed an industrial miracle. Into this race stepped Henry J. Kaiser, a civilian contractor with no naval background, but with a talent for reorganizing chaos. Kaiser had built dams, highways, and bridges, but never a ship. What he understood, however, was flow, how to move men, machines, and materials through space like an assembly line. His confidence bordered on arrogance. Yet within months, he was overseeing new yards in Richmond, California, and Portland, Oregon, massive facilities rising from mudflats at breathtaking speed. Kaiser's approach was radical. He rejected the old, slow art of sequential shipbuilding and replaced it with industrial logic, prefabrication. Every hull would be built in sections: bow, stern, deckhouses, and cargo holds, all constructed separately, then welded together like pieces of a puzzle. His engineers called it modular assembly, but the workers simply called it faster. Still, the true revolution was not in how the ships were divided, but how they were joined. Traditional riveting required teams of skilled men working in pairs, one heating and tossing red-hot rivets, the other hammering them tight. It was laborious, deafening work. Welding, by contrast, fused metal through heat alone. It eliminated the holes, the bolts, and the fatigue cracks that rivets often caused. The technique had existed for years, but few shipbuilders trusted it on such massive structures. Kaiser did. To the old guard, welding seemed reckless, a shortcut that could end in catastrophe. But to Kaiser's engineers, it was liberation. Without rivets, a ship's hull became a continuous skin of steel, lighter yet stronger. Welders could be trained in weeks instead of years, opening the door for women and unskilled workers to join the war effort. The process required no artisans, only discipline, precision, and electric current. By the summer of 1942, Kaiser's yards were humming. Trains delivered prefabricated plates. Cranes lifted them into assembly lines. The clang of hammers gave way to the hiss of torches. A Liberty ship that had once taken 7 months now left the slipway in under 2. The transformation was staggering. Each yard functioned like a living organism, thousands of people moving to a single heartbeat of urgency. Still, the shortcut carried a cost. Welding was faster, yes, but it demanded consistency. Poor technique could leave microscopic cracks that spread unseen through the hull. Early welders, driven by speed, quotas, and exhaustion, sometimes cut corners. Reports of fractures began to surface, especially in the cold Atlantic, where brittle steel met freezing water. But for every failure, 100 ships survived, enough to prove that the experiment worked. What began as desperation had turned into domination. By 1943, Liberty ships were appearing faster than submarines could sink them. Kaiser's shortcut, a simple act of replacing rivets with welds, had rewritten the rhythm of war. Yet few outside the shipyards understood what it took to make that miracle real. Behind the speed lay a relentless learning curve, a human tide of welders, foremen, engineers, and planners who fought not with weapons, but with time itself. It was in this crucible of urgency that one civilian discovered how to turn months into days, and how a single weld could change the outcome of a world war. The shipyards that rose along America's coast in 1942 were unlike anything the world had ever seen. They weren't just construction sites. They were industrial cities born overnight. In Richmond, California, Henry Kaiser's yard sprawled across the shoreline like a mechanical landscape. Conveyor belts carried steel plates from railcars straight to fabrication sheds. Overhead, cranes glided silently through the night, lifting tons of metal as easily as a carpenter lifts wood. Floodlights turned darkness into day, and workers, men, women, migrants, veterans, poured through the gates in shifts that never ended. Every spark, every torch, every roar of machinery was part of a single race to outbuild the sea itself. At the heart of this revolution lay one deceptively simple change: continuous welding. Until then, ship hulls were mosaics of riveted joints, each a potential weak point and time sink. Welding, however, allowed for seamless bonds. Instead of drilling holes and driving rivets, steel plates could now be joined edge to edge, creating one continuous skin. The process was not only faster but stronger and lighter. In the old days, building a ship meant drilling 2.5 million holes. In Kaiser's yards, that number dropped to almost zero. The difference translated into time, and in wartime, time was blood. The method that truly transformed production was called submerged arc welding, an automated system that used a continuously fed wire electrode and a protective layer of flux to shield the molten pool from the air. The arc remained invisible beneath the granular flux, preventing oxidation and ensuring smooth, uniform seams. Unlike manual welding, this could run continuously for meters at a time without stopping. To the engineers, it was a miracle of consistency. To the foreman, it was the difference between finishing in 230 days or in less than 30. Prefabrication made it even faster. Instead of assembling ships piece by piece on a single slipway, entire sections, the bow, midship, stern, and deck houses, were built separately in different workshops. Each section was fully outfitted with pipes, electrical wiring, and insulation before being moved by crane to the launching berth. There, welders joined the pieces together in a matter of hours. It was shipbuilding turned upside down, the factory model brought to the waterfront. But progress didn't come easily. Welding at such a scale required a new kind of workforce. Many of the men who once drove rivets were gone, enlisted, or drafted into combat. Their replacements were a generation of trainees, many of them women who had never held a torch before. They were called Kaiser's welders, tens of thousands strong, recruited from every corner of the country. Training schools taught them to read blueprints, handle arc guns, and master the delicate balance between heat and speed. Mistakes were costly, yet the learning curve was astonishingly steep. Within months, these new welders were producing seams that met Navy inspection standards. Every Liberty ship became a symbol of civilian power. The yards worked with military discipline but civilian spirit, improvisation, innovation, and stubborn pride. Supervisors constantly refined the workflow, minimizing idle time, reorganizing teams, and applying statistical controls to reduce errors. Kaiser's secret wasn't just the welding itself, it was process engineering. He applied lessons from his dam projects to the shipyard floor. Divide the task, standardize it, and repeat it endlessly until perfection becomes routine. Still, there was resistance. Many naval architects doubted that welded ships could survive the brutal stresses of the open sea. Riveting, though slower, had proven reliability over decades. Welding was untested on this scale. Yet desperation left little room for tradition. Each successful launch silenced another critic. And when the first all-welded Liberty ships crossed the Atlantic without incident, the skeptics began to fade. By late 1942, Kaiser's shortcut was no longer a gamble, it was gospel. What had begun as an experiment became the new standard for American shipbuilding. Yards that once measured success in months now counted in days. New techniques spread like wildfire. Traveling cranes, rolling assembly lines, and specialized jigs that locked hull plates into position with precision. Even the Navy, initially skeptical, began to embrace welding for its combat ships. But the ultimate test was still to come. Welding had given speed, yet the question remained, how fast could they truly go? Could a shipyard, with nothing more than organization, electricity, and human will, collapse a half-year process into a single week? The answer would come in the form of one record-breaking experiment, a demonstration so spectacular that it would capture headlines around the world and prove that the shortcut was not just faster, but revolutionary. Every revolution in war industry carries within it the story of people, ordinary civilians who suddenly found themselves at the edge of history. In Kaiser's shipyards, that transformation was visible in every direction. The human angle was not about generals or admirals, but about welders, men and women whose hands became the instruments of America's industrial might. They came from farms, factories, and schools, many with no technical background at all. Posters urged them to build ships, defend freedom, and they answered by the tens of thousands. Training programs turned novices into skilled welders in just a few weeks. A young woman who had never held a tool might, within a month, be responsible for fusing critical seams on a ship that would cross the Atlantic. This new workforce worked around the clock, often 6 or 7 days a week, through exhaustion and noise. Yet they found pride in the sparks, each one a contribution to victory. Their fatigue was outweighed by a simple truth. Every weld meant supplies, soldiers, and hope moving toward Europe. The process itself was a study in precision and rhythm. Shipbuilding had once been a linear act, keel first, hull second, fittings last, but Kaiser's engineers broke the chain. They introduced assembly line logic into a world that had never known it. Hull plates were cut and shaped miles away from the slipway, using standardized templates and mechanized cutters. Subassemblies were welded into large blocks that could be lifted directly onto the hull frame. Instead of one crew working for months, hundreds of teams worked in parallel, each responsible for a single repeated task. Efficiency became art. Every step was timed, measured, and refined until the process itself became predictable, an industrial symphony of motion and heat. Technological advancement was the backbone of this transformation. The automatic submerged arc welding technique changed everything. Before, manual welders struggled with fatigue and inconsistency. But now, an electric arc, guided mechanically beneath a blanket of flux, could maintain an unbroken weld for hours without interruption. The result was a seam stronger and smoother than any hand-driven rivet line. Automation allowed the shipyards to maintain relentless output without sacrificing accuracy. The machines hummed day and night, consuming steel, wire, and electricity at unprecedented rates. For the first time, engineers could design ships with continuous stress paths, removing the rivet holes that had once weakened hulls. The ships were not just faster to build. They were also, on paper, structurally superior. But the breakthrough went beyond technology. It was about throughput. The genius of the Liberty Ship program lay in its ability to scale. Each yard was not an isolated operation. It was part of a synchronized network. If one facility needed a component, another supplied it. Standardization allowed parts to be interchangeable across the entire program. Kaiser's Richmond yards built engines for Portland. Portland shipped deckhouses to Los Angeles, and Los Angeles sent boilers to Richmond. Everything fit because everything was standardized down to the millimeter. This was the first time in naval history that ships were treated not as custom works of art, but as reproducible products. The mindset echoed Detroit's assembly lines. Only instead of cars, they were building the very vessels that would deliver tanks, jeeps, and aircraft overseas. Still, speed brought new challenges. Welding's simplicity masked its hidden risks. A bad weld could look perfect on the surface, but conceal dangerous microcracks beneath. Under the freezing stress of the North Atlantic, these flaws could propagate and split the steel. When the first fractures appeared, the headlines were immediate: welded ships breaking apart in storms, hulls snapping cleanly in two. Critics blamed the shortcut, arguing that the old riveted ships would never have failed so catastrophically. Investigations followed, and metallurgists discovered that the issue lay not in the welding alone, but in the combination of brittle steel and temperature shock. The Liberty ships were built for speed, not for Arctic cold. Kaiser's engineers adapted swiftly. They revised welding procedures, improved inspection standards, and changed steel composition to resist low-temperature brittleness. Quality control teams used X-rays to scan critical seams, while training centers emphasized proper preheating and cooling techniques. Every failure became a lesson that refined the process. Despite the setbacks, the data was clear. Welded ships could be produced 5 times faster and at lower cost, with acceptable reliability for wartime needs. It was not perfection, it was momentum. Beyond the factories, the effect rippled through the war effort. The Liberty Ship program proved that civilian industry could outpace destruction. Each shortcut, each spark of innovation, translated into convoys that arrived safely in Britain, the Soviet Union, and beyond. By early 1943, the balance in the Battle of the Atlantic began to shift. U-boat captains reported endless new targets, and even when they sank one, 3 more took its place. The Germans called it the endless tide. The Allies called it victory by production. The welding shortcut had not only changed the pace of shipbuilding, it had redefined warfare itself. Logistics had become a weapon, and the factory floor was the new front line. Every innovation carries its shadow, and the welding revolution was no exception. The very speed that made Liberty ships a miracle of production also exposed their most dangerous flaw: metallurgy. Engineers began to realize that steel, like men, has limits under pressure. At normal temperatures, the welded hulls were resilient and flexible. But in the icy Atlantic, where temperatures plunged below freezing, the same steel became brittle. When combined with the sharp corners of hatch openings or square-cut joints, stress fractures could propagate like cracks in glass. Ships that had sailed perfectly from the West Coast sometimes broke apart mid-voyage in the North Atlantic storms, snapping clean in two without warning. The failures horrified the engineers, but they refused to retreat to the slower methods of riveting. Instead, they studied, tested, and learned. Metallurgists traced the problem to low ductility steel and poor weld control. They introduced preheating procedures, stress relief techniques, and new steel alloys with added manganese to resist brittleness. This shortcut had forced science to evolve at the same pace as industry. While metallurgy fought its silent battle, strategy was being reshaped at sea. The Liberty ship was not glamorous. It was slow, noisy, and defenseless, but its numbers became a strategic weapon. For every U-boat commander who celebrated a sinking, the Allies launched 2 replacements. These ships carried everything: grain, tanks, munitions, and fuel. Each vessel welded together in Kaiser's yards became a lifeline stretching from American ports to the front lines of Europe, Africa, and the Pacific. As Winston Churchill later remarked, "The foundation of all our victories rests upon the immense output of the American shipyards." Welding, the so-called shortcut, had done what no fleet of warships could. It overwhelmed the enemy with abundance. The enemy angle itself is worth remembering. German intelligence tracked the Liberty ship program with disbelief. Early reports dismissed it as propaganda, impossible production rates, exaggerated claims. But when reconnaissance confirmed hundreds of new hulls moving from ports each month, German Naval Command realized they were fighting an industrial hydra. Sink one head, and 2 more would rise. The Kriegsmarine's U-boat fleet, once the terror of the Atlantic, found itself stretched thin and demoralized. Even Admiral Donitz, the architect of the U-boat campaign, conceded that the Allies' industrial scale had nullified Germany's tactical advantage. Welding, automation, and prefabrication had transformed warfare into a contest of manufacturing endurance. One Germany could no longer win. From the leadership perspective, the Liberty ship program revealed something profound about management during war. Henry Kaiser was not a traditional commander. He wore no uniform, yet his authority in the industrial battlefield was absolute. He redefined leadership through empowerment and trust. Where others demanded obedience, Kaiser demanded ideas. He encouraged foremen to experiment, to test new jigs, to rearrange workflows if it saved even an hour. Mistakes were expected. Stagnation was not. The same ethos trickled down to the workers. Everyone knew they were part of something historic, not just building ships, but building the very logistics of victory. This leadership style contrasted sharply with the bureaucratic rigidity of older government contractors. While traditional naval yards insisted on perfection before launch, Kaiser prioritized iteration: build, launch, learn, improve. Each new ship became a prototype for the next. What mattered was not flawless craftsmanship, but continuous acceleration. In the language of war, it was the difference between a cautious retreat and a relentless advance. This mindset, borrowed from civilian construction, proved revolutionary. By the time bureaucracies debated standards, Kaiser's welders were already breaking records. There was also a moral dimension to this shortcut. It wasn't only about efficiency, it was about inclusion. For the first time in industrial history, women and minorities entered skilled trades at scale. The welding torch became a symbol of opportunity. African-American men and women who had been barred from unions found jobs in the yards. Women who had been homemakers became specialists in metallurgy, inspection, and fabrication. The shipyards became a social experiment, proving that patriotism and skill had no gender or color. In a time when much of the world was divided by hate and ideology, the Liberty ship program stood as quiet proof that unity could be engineered, one spark at a time. The final angle was perhaps the most philosophical: the moral psychology of production under pressure. Every shortcut carries suspicion, the fear that faster means weaker, that efficiency compromises integrity. But in Kaiser's shipyards, the shortcut became a moral victory. It was not about skipping steps, but about reimagining them. The welders did not cheat the process, they reinvented it. Where others saw risk, they saw potential. Each glowing seam was a statement that human ingenuity could overcome even the tyranny of time. In that sense, welding became a metaphor for the entire war effort, the fusing of millions of individual efforts into one unbroken line of resistance. By 1943, the lessons from these angles, human, technological, strategic, moral, had fused into something unstoppable. America had learned to treat time as a weapon. The only question left was how far that weapon could go. The next great experiment would answer that, and it would stun the world with a single, record-breaking feat of speed and precision. The morning of November 8th, 1942, dawned cold and gray over the Richmond Shipyard No. 2. The yard buzzed with a kind of controlled chaos that bordered on disbelief. Word had spread like wildfire that Henry Kaiser's team was attempting the impossible, to build and launch a full Liberty ship in less than 5 days. No one outside the project believed it could be done. Even many inside the yard thought it was madness. But in wartime America, madness often masqueraded as genius. The ship they would build was named SS Robert E. Peary, and in the next 4 days and 15 hours, it would become a legend. The challenge wasn't merely symbolic. It was a proof of concept, a demonstration of what could happen when every lesson of welding, prefabrication, and process engineering converged. Thousands of workers volunteered for the record run. The shipyard clock was set, radio crews arrived to document the feat, and newspapers sent photographers to capture what they expected to be a publicity stunt. But as the sparks began to fly, even the skeptics went silent. At 12:01 a.m., the first shift began laying the keel plates, guided by precision jigs and templates. Giant cranes swung overhead, lowering prefabricated sections, each already welded, fitted, and painted into perfect alignment. The process was choreographed like a ballet of steel. Teams moved in perfect timing. Welders crawled across seams before the previous joint had cooled. Forklifts, cranes, and fitters worked in relentless sequence, every minute accounted for. There was no margin for hesitation. By dawn on the second day, the hull was already taking shape. Workers called it the steel miracle. Subassemblies that once took weeks to complete were now being hoisted into place every hour. Entire deck sections arrived pre-wired, pre-piped, and pre-tested. The innovation was astonishingly simple. Instead of waiting for one team to finish before another began, everyone worked simultaneously. Electricians, pipe fitters, carpenters, and welders overlapped their tasks in perfect synchronization. It was less like shipbuilding and more like orchestrating a mechanical symphony. The tension was immense. Reporters noted that sleep-deprived supervisors moved through the yard with stopwatches, shouting times, adjusting crews, making real-time corrections. The cafeteria stayed open 24 hours a day. Coffee flowed like oil. Yet morale was high. The welders had adopted a kind of fanatic pride. They didn't see themselves as workers anymore. They were soldiers of the home front. Each seam of molten metal, each completed joint, was a bullet fired at fascism. By the end of the third day, the impossible seemed within reach. The Peary's hull gleamed under floodlights, her outline unmistakable against the Pacific sky. Inspectors moved from bow to stern, checking seams for warping or slag inclusions. Remarkably, defects were minimal. The automated welding systems had done their job. The only sound that broke the monotony was the rhythmic clanging of steel plates cooling, a heartbeat of industrial triumph. Kaiser himself visited the yard that evening, his overcoat dusted with metal shavings. He didn't speak to the reporters. He didn't need to. The sight before him, 250,000 parts becoming a ship in less than a week, said everything. When asked how it was possible, one foreman replied simply, "We stopped waiting for perfection and started building for purpose." Day 4 began with rain. The ground turned slick, welders worked beneath makeshift tarps, and cranes groaned in the damp air. But no one slowed down. The workers had turned the schedule into a matter of pride. Entire neighborhoods in Richmond sent food and music to the yard. Families gathered outside the gates, cheering the crews as if they were soldiers returning from battle. The local radio announced hourly progress updates, turning a ship launch into a national event. By the evening of November 12, 1942, the SS Robert E. Peary stood complete, 441 feet of steel assembled in 4 days, 15 hours, and 30 minutes. Her hull number was still warm from the last weld when the ceremonial flags were raised. Reporters timed it down to the second. At 4:01 p.m., the massive ship slid down the greased ways and into the San Francisco Bay. The roar of the crowd echoed across the harbor. Never before in human history had a vessel of that size been built so fast. For the onlookers, it was a spectacle. For the shipbuilders, it was proof. The shortcut, welding, modular construction, and continuous flow had not only worked but shattered every assumption about what industry could achieve. The Peary didn't just float. She sailed, fully seaworthy, carrying her first load of cargo weeks later. The newspapers called it the 4-day ship, but to those who built her, she was something more, the embodiment of American urgency. When the last crane swung away and the final torch went dark, Kaiser's men stood silent, their faces illuminated by the ship's reflection on the water. It was as if they were staring at time itself, time they had captured, compressed, and transformed into steel. That record would never be broken, and it didn't need to be. The experiment had done its job. From that day forward, the world knew that the old limits of industry had vanished. When the SS Robert E. Peary slipped into the waters of San Francisco Bay, it wasn't merely a ship launch, it was a declaration of industrial supremacy. The feat stunned even the most hardened skeptics within the U.S. Navy and War Department. Before the Peary, constructing a Liberty ship required more than 200 days on average. Now, one had been completed in under 5. Though the 4-day ship had been meticulously pre-planned, with every part staged and every worker coordinated to the minute, it demonstrated something far greater than speed. It showed that America's industrial machine had reached a level of precision and adaptability that no other nation could rival. The moment news broke, telegrams and newspaper headlines echoed around the world. Ship built in 4 days. New record in history of shipbuilding, read the New York Times. Crowds gathered at post offices and factory bulletin boards to read the story. To the average American, it was proof that the home front could achieve miracles of its own. For the workers, it was validation the sleepless nights, the burns, the exhaustion had all been worth it. To Henry Kaiser, however, the Peary was only the beginning. He saw it not as a stunt, but as a system, one that could be replicated, scaled, and refined. After the Peary's launch, the Maritime Commission began implementing Kaiser's principles across dozens of yards nationwide. They adopted modular construction, round-the-clock shifts, and the now standardized continuous welding line. Shipyards that had once launched a few vessels a year were now producing one every few days. In Portland, a yard set a new internal record, a complete ship in just over 6 days. In Savannah, New Orleans, and Baltimore, similar achievements followed. The curve of production rose exponentially. By 1943, the United States was launching more tonnage each month than Germany could sink. Yet the success brought new challenges. The Robert E. Peary had been built under near-perfect conditions, mild weather, full staffing, and carefully staged prefabrication. Reproducing that performance in ordinary conditions proved difficult. Most Liberty ships still took several weeks to complete. But that wasn't the point. What mattered was that the theoretical limit had been shattered. The psychological barrier, the belief that a cargo ship required months, was gone forever. The 4-day record became the new standard of ambition. It wasn't expected to be repeated. It was meant to inspire. Kaiser's management philosophy spread beyond shipbuilding. His speed through organization approach began to influence aircraft production, tank factories, and even the Manhattan Project's infrastructure. The idea that complex engineering tasks could be reduced to modular, repetitive, and scalable processes became a cornerstone of modern manufacturing. What Ford had done for automobiles, Kaiser had done for war. The Peary's launch marked the birth of industrial acceleration, a concept that would define the second half of the 20th century. Meanwhile, on the front lines, the results were immediate and measurable. In 1942, Allied convoys struggled to maintain supply lines across the Atlantic. U-boat wolf packs tore through merchant fleets, sinking hundreds of ships each month. But by 1943, those same routes began to thicken with new hulls. Every ship that sank was replaced, sometimes twice over, within weeks. The flow of material became unstoppable. Fuel, ammunition, food, and vehicles moved continuously from American ports to European beaches. Operation Torch, the invasion of North Africa, was sustained entirely by Liberty ships. Later, During D-Day in 1944, over a quarter of the invasion supplies crossed the channel aboard ships that had been built using Kaiser's welding shortcut. Admirals and generals began to realize that logistics, not battleships, not bombers, were winning the war. A Liberty ship might not carry a gun, but it carried the war itself. Each vessel symbolized a simple equation. Faster builds meant shorter wars. The welding shortcut had transformed industrial production from an art into a weapon. It was the first time in history that a nation's factory floor became its front line. For the workers who had built the Peary, the pride never faded. Years later, many still recalled the moment she touched the water, the cheer that rolled across the bay, the sense that they had bent reality itself. Some welders wept openly. They knew that no single ship could win a war, but they also knew that speed, multiplied by thousands, could. The Peary's launch had proved what America was capable of when time itself became the enemy. The aftermath of the record echoed long after the war ended. The Liberty ship program had not only outpaced the U-boats, it had transformed the very concept of industrial warfare. Nations no longer fought only with soldiers and guns, but with engineers, welders, and production lines. Speed was no longer a luxury, it was survival. In the weeks following the launch, Kaiser met with Washington officials who still viewed him as an outsider. They congratulated him, then cautioned him about sustainability. "It's not about one miracle," one bureaucrat said. Kaiser smiled and replied, "It's about learning to perform miracles every day." And for a time, America did exactly that. The 4-day ship was never repeated, but its legacy persisted in every hull that left the slipway afterward. The Liberty ship program would eventually produce 2,710 vessels, more than any single class of ship in history. And it all began with one shortcut, one idea, and one man who refused to accept that time was fixed. The record-breaking launch of the Robert E. Peary was the turning point, not just in the war, but in the way humanity understood production itself. The shortcut had become the strategy. What remained now was to see how this revolution in speed would shape the end of the war and the new world waiting beyond it. When the roar of the Robert E. Peary's launch faded and the workers finally laid down their torches, America stood on the threshold of a new industrial era. The success of the Liberty ship program did more than fill the oceans. It filled the Allied war effort with confidence. By the beginning of 1943, Kaiser's system of welded, prefabricated construction had spread across every major shipyard on both coasts. From Maine to California, assembly lines of steel operated day and night, producing cargo ships faster than any enemy could destroy them. The war of attrition at sea had turned decisively in the Allies' favor. In January 1943 alone, U-boats managed to sink over 100 Allied vessels. But that same month, American shipyards launched nearly 140 new ships. The tide had shifted. For the first time since the start of the war, production was overtaking destruction. What had once seemed an endless deficit of tonnage now became a surplus. Convoys to Britain grew larger, more frequent, and better protected. Supplies reached the Soviet Union through Arctic routes, sustaining the Eastern Front through brutal winters. The Liberty ship had become the lifeline of the free world, unglamorous, slow, but unstoppable. The numbers tell the story. By the end of 1943, Liberty ship output reached an astonishing 140 ships per month. Between 1941 and 1945, America launched a total of 2,710 Liberty ships, the largest class of ships ever built. The average construction time fell from 230 days to just 42. At Kaiser's yards, it was even lower. In one 12-month period, his team launched 747 ships, averaging more than 2 every single day. It was a pace of production unmatched in maritime history. The cost per ship plummeted, too. What once required millions of dollars and months of labor could now be built for a fraction of the time and expense. But the impact wasn't only economic or military. The shipyards themselves became engines of social transformation. They employed over 1.5 million workers, including hundreds of thousands of women and minorities. Entire communities were born around these industrial hubs. Richmond, California, for instance, swelled from a quiet town of 20,000 to a wartime city of over 100,000 residents. Schools, hospitals, and housing projects sprang up almost overnight. The shipyard wasn't just a workplace, it was a civilization built around purpose. The phrase home front hero took on a literal meaning. These workers, once dismissed as ordinary civilians, had proven they could match the endurance of soldiers. Kaiser himself became a national symbol of efficiency. Journalists dubbed him America's miracle builder. He moved with the same tireless energy that defined his projects, overseeing shipyards one day, attending Washington briefings the next, and visiting training schools the day after. But his true genius lay not in machinery, but in management. He treated logistics as a living organism. Every worker, every part, every spark was a vital cell in a vast body of coordination. His philosophy of continuous flow changed industrial thinking forever. The Liberty ships soon became a common sight in every ocean, their blocky silhouettes lined up in convoys stretching to the horizon. They carried tanks for Patton, rations for Montgomery, and ammunition for Eisenhower. Their cargo sustained the invasions of Sicily, Normandy, and the Philippines. Whenever a Liberty ship was lost, another took its place before the sea had time to calm. Sailors who once doubted the welded hulls began to trust them, knowing that despite their simplicity, these ships were durable, reparable, and, above all, replaceable. The greatest consequence, however, was psychological. The shipbuilding miracle proved that speed, once the enemy of quality, could become its ally when guided by discipline and design. It shattered the myth that mass production was the domain of consumer goods alone. Now, even the most complex machines, ships, bombers, tanks, could be built with assembly line precision. America's industrial heart had become its most powerful weapon. The Liberty ship's legacy was measured not only in steel, but in morale. It told every factory worker, every welder, and every foreman that they, too, were fighting the war. And with each launch, they proved that the battle for time, the race to build faster than destruction, could indeed be won. Victory at sea came not through a single battle, but through the relentless rhythm of production, a rhythm the Liberty ship had perfected. Yet behind the triumph, the engineers and scientists continued to wrestle with the lessons of speed. As 1944 progressed, a troubling pattern began to emerge. A small number of welded ships, particularly those operating in frigid northern waters, suffered catastrophic hull fractures. The failures were sudden and complete, a clean break from deck to keel. Though the number was statistically minor compared to total production, each incident prompted urgent investigation. For engineers, it was a humbling reminder that innovation always carries consequences. Teams from the U.S. Navy, the Maritime Commission, and research laboratories gathered evidence, hauling fractured sections ashore to study the metallurgical causes. The findings revealed the complexity of the issue. The problem wasn't poor workmanship or design. It was brittle fracture, a phenomenon few had encountered on such a scale. Under freezing temperatures, certain batches of mild steel lost their ductility. Instead of bending under stress, they cracked like glass. The combination of low temperatures, square-cut joints, and rapid welding had created conditions ripe for failure. It wasn't the shortcut itself that was flawed, but the material science that hadn't yet caught up with it. The response was immediate. Metallurgists developed new steel specifications with higher manganese content and tighter carbon control, reducing brittleness. Shipyards adopted rounded corners for hatches and reinforced critical weld zones. X-ray inspection became standard practice, allowing microscopic flaws to be detected before launch. Welding schools revised their training to emphasize heat control and cooling cycles. Within months, fracture incidents dropped dramatically. The crisis that had once threatened to tarnish the Liberty ship's reputation instead propelled the greatest leap in metallurgical understanding of the 20th century. What began as a setback became a foundation for modern standards in structural steel design, lessons that would influence bridges, pipelines, and skyscrapers for decades. As the war neared its end, the full scale of the Liberty ship's impact became clear. These vessels had transported roughly two-thirds of all Allied cargo across the Atlantic. They carried nearly every supply item used in Europe's liberation, from canned rations to Sherman tanks. The logistics of victory, the movement of men, food, oil, and ammunition, rested on the welded skeletons of these unassuming ships. When the Allies landed in Normandy on June 6, 1944, hundreds of Liberty ships anchored offshore served as floating depots, hospitals, and supply stations. Without them, the invasion's success would have been impossible. After 1945, the surviving Liberty ships entered a new chapter. Many continued in commercial service for decades, ferrying goods across peaceful seas they had once crossed under fire. Others were sold to foreign navies, converted into troop transports or training vessels. A few, like the Jeremiah O'Brien and the John W. Brown, were preserved as museum ships, living monuments to the men and women who had built them. The rest met quieter fates, dismantled for scrap or left to rust in forgotten harbors. Yet even as their steel faded, their legacy endured. The post-war era adopted Kaiser's philosophy as gospel. Modular construction, continuous welding, and process flow became standard across industries. The aviation boom, the interstate highway system, even nuclear power plant construction, all borrowed from the methods first perfected in those wartime yards. The notion that a project could be accelerated not by cutting corners, but by reorganizing them, became central to modern engineering. This shortcut had evolved into a science. For the millions who had labored under the sparks of wartime urgency, the legacy was deeply personal. The shipyards had changed their lives, teaching skills, creating equality where there had been none, and proving that civilians could achieve military miracles. For Henry Kaiser, the experience became a lifelong crusade for progress. After the war, he applied the same principles of efficiency and compassion to build hospitals, housing projects, and the pioneering Kaiser Permanente health system. He had once welded ships, now he welded communities. By the late 1940s, the world stood on the edge of a new industrial dawn. The Liberty ship had done more than shorten a war. It had redrawn the boundaries of what humanity could build when purpose overpowered hesitation. From every rivet replaced by a weld, a lesson remained. Speed, when guided by understanding, was not recklessness, it was strength. In the quiet years after the war, long after the torches cooled and the slipways emptied, the story of the Liberty ship remained one of humanity's most extraordinary industrial triumphs. It wasn't a tale of generals or admirals, but of welders, engineers, and ordinary men and women who discovered that time itself could be conquered. The shortcut that once seemed reckless had proven to be a revelation, not because it cut effort, but because it redefined it. What Henry Kaiser and his civilian army achieved in those feverish years was nothing less than the transformation of industry into art, precision, and unity. The Liberty ship was more than steel and cargo. It was a philosophy forged in urgency, that problems too vast for individuals could be solved by collective will and innovation. Every welded seam carried the fingerprints of a society determined to survive. Each ship launched was a testament to a nation that refused to accept limits, that understood war was not only fought with weapons, but with ideas. The unbroken line of weld across a Liberty ship's hull symbolized something larger, the seamless bond between ingenuity and necessity, between speed and endurance. In a sense, the Liberty ship was the bridge between two worlds, the age of craftsmanship and the age of systems. It proved that efficiency did not have to mean soullessness, and that progress, when guided by purpose, could serve humanity rather than consume it. The lessons learned in those shipyards of modular construction, cross-disciplinary teamwork, and continuous improvement became the DNA of modern manufacturing. The Liberty ship was the ancestor of every prefabricated structure, every assembly line that built not just machines, but futures. When one looks today at the surviving Liberty ships, preserved in quiet harbors, their gray hulls still bear the scars of war and time. Yet beneath those scars lies something eternal. The echo of sparks, the hum of arc welders, the laughter and grit of workers who refuse to yield. They remind us that history is not only written by those who fight on the front lines, but also by those who build the ships that carry them there. The welding shortcut began as an experiment in speed, but it ended as a testament to vision. It showed that with courage, coordination, and belief in human hands, even the boundaries of time can be bent to serve the cause of freedom.